In this video, we'll talk about some basic properties of matrix multiplication. So matrix multiplication has a lot of really nice properties, just like real number multiplication does, but there is one particular one that it does not have. So first, what does it have? So matrix multiplication is associative. This means that if I have three matrices A, B, and C, for which the following products are all defined, then A times B and then times C is the same as A times B times C. So if you have the product A, B, C, it doesn't matter if you do the A times B first and then the C, or the BC first then the A, they'll both give you the same answer. It is also distributive. So A times the sum of B and C is the same as AB plus AC, and A plus B times C is AC plus BC. And the main reason I wrote this one twice is because the property that this operation does not have, and that's that it is not commutative. That means that AB is not necessarily equal to B times A. You cannot switch the order of matrices. This also sort of makes sense in terms of the definition of multiplication, in the sense that we need dimensions to line up to make this work. And it's possible for only one of these two to be defined based on dimensionality. For instance, if A is dimension n times m, and B is dimension m times p, then the product AB is defined because the inner dimensions match, the m and the m, but BA may not be defined because P might not equal n. And we'll do an example of this in a little bit. The other thing to discuss briefly here is the idea of matrix vector multiplication. And the idea is that for a vector V, if it's an n-dimensional vector, we can think of this as a column vector as an n row by one column matrix. And in that sense, any matrix with n columns, I can multiply by this vector. So if A was an m by n matrix, and V is our n-dimensional vector, n by 1 vector, then the product AV is defined and is an m by 1 vector. The reason why I bring this up is to mention the fact that we can multiply matrices by vectors if the dimensions match up. In particular, I can multiply an m by n matrix by an n vector, and it turns it into an m vector. So matrices give us a way to turn one vector into another by multiplication. In particular, we can think about also defining matrices from the outset as linear maps on vectors, which was done in a separate video. And because matrix multiplication by itself is distributive, so is this. So for instance, A times vector V plus vector W is the same as A times vector V plus A times vector W. And really all the nice properties you want to hold happen for the case of matrix vector multiplication. So for an example, let's compute these two products, A times B and B times A. So A times B, I'll first rewrite the matrices. And this product should then be row 1 of A times column 1 of B put together. So I'll see 1 times 3 is 3, plus 5 times minus 1 is minus 5. Then row 1 of A, column 2 of B, in the purple spot here. 1 times 4 is 4, plus 5 times 2 is plus 10. Row 2 of A, column 1 of B, in the pink spot, will give me 3 times 2 is 6, minus 1 times minus 1 is plus 1. And then row 2 of A, column 2 of B, to put in the orange spot, 2 times 4 is 8, minus 2. The product I get here is minus 2, 14, 7, and 6. And we do the same for B times A. Now switching the order of the matrices. And for our product we get in the first spot, 3 times 1 plus 2 times 4. First row, second column, 3 times 5 plus 4 times minus 1. Second row, first column is minus 1 plus 4. And the second row, second column is minus 5, minus 2. So we get 11, 11, 3, and minus 7. And so we can clearly see these two matrices here are not the same. So this is an example of how we know that multiplication here is not commutative because I can't swap the order and get the same answer out at the end. But all the other properties hold very nicely. So that's the idea of matrix multiplication, some of the properties that it has and that it doesn't have, which are important to know as we start to do more common things with matrices in the future.